CLI and a cross-platform IDE for C and C++. Download now.
All right, let's get started. Hello, everybody. My name is Tsung-Wei Huang, and you can just call me TW. Today, I'm going to talk about dynamic asynchronous tasking with dependencies. This is a project to help you parallelize your application more easily. This is what I'm going to do for today's talk. We are going to understand the importance of asynchronous tasking with dependencies and recognize the limitations of existing asynchronous tasking models. Then we will introduce a new dynamic task graph programming model called AsyncTask and overcome the scheduling challenges to support our model. Finally, we will demonstrate the efficiency of our model and conclude the talk. You probably already know parallel computing has advanced many of our application performance to a new level that is previously out of reach. For example, if you want to train a machine learning model with 40 CPUs, you can get 10x speed up. With one GPU, you can bring another 10x speed up. More importantly, modern hardware has been designed to run in parallel for performance. For example, here I'm showing you an Intel Haswell microarchitecture, which is released in 2013. This architecture typically comes with 4 cores and has one integrated GPU. It is based on a superscalar architecture that can issue and complete multiple independent instructions per cycle. It also supports hyper-threading technology that allows a single physical CPU core to appear as 2 logical processors to the operating system. So the key takeaway over here is if you don't do parallel programming, you are not utilizing your hardware efficiently. However, today's parallel computing problems are very complicated and irregular. Here, I'm showing you a computational task graph of a GPU-accelerated circuit simulation workload. The task graph models a GPU operation as an asynchronous task and the dependency between 2 GPU operations in an edge. This computational task graph can be very, very large. In this example where we are simulating an NVIDIA deep learning accelerator design of 500 million gates, it has more than 1,000 asynchronous task kernels and dependencies. Even with the GPU, it can still take several hours to finish. This is another example of irregular parallel computing problems where we are parallelizing the VLSI circuit timing analysis workload using many core CPUs. The analysis algorithm is modeled as a task graph that propagates the timing values from the inputs of the circuit all the way to its outputs. For very large design, the resulting task graph can contain more than 100 million asynchronous tasks and 150 million task dependencies. That is very, very huge. Turns out, if you would like to parallelize this type of irregular problem, it's not very easy because you always have to deal with a lot of technical details such as parallelism abstraction, over software, hardware, concurrency control, scheduling efficiencies, you gotta worry about performance portability and productivity and so on and so forth. And there is always this trade-off between what you want and the cost of that intent. For example, everybody wants simple, maintainable, extensible, and portable implementation, right? But each of that intent comes at the cost of performance. So we want a solution that can sit on top to help us manage as much of the technical details as possible, because programmers really care how fast they can get things done. By fast, I mean both performance and productivity. Among various solutions, task parallel programming, or TPP, has shown promise to be an effective solution, particularly for irregular workloads, because it allows us to capture developers' intention in decomposing an algorithm into a top-down task graph, while you can delegate scheduling details that are very difficult to program correctly, such as load balancing, concurrency control, to an optimized scheduling runtime. That is why exactly over the past few years, we are seeing a growing number of parallel programming libraries moving toward task parallelism, such as OpenMP's task dependency clauses, C++26 execution control library ECL, TPP flow graph, and task flow. Now we are going to look into some popular asynchronous tasking model and their limitations. In C++, we can create an asynchronous task using stud async, which is a high-level standard library facility for you to launch a task asynchronously. For example, here I have a function, compute, that does nothing but returns an input argument. We use async to asynchronously run the function compute on a new thread. And that std async will return a future object for us to wait for this asynchronous task to finish and access its result. In this case, it will be 42. Very simple. This is an example implementation of std async. We have two templates, one on the function type and another on the argument types. First, we will get the return type of a function and use it to create a promised future pair for inter-thread synchronization. So basically, I promise you that I will run your function and you can access the result from the future object. Next, we create a thread from the lambda that captures function and its arguments and invoke the function in the body. Then we detach the thread to mimic the fire and forget behavior of std async. Finally, we return the future to the caller. With std async and std future, we can build a task graph to handle asynchronous tasking with dependencies. This is because std future allows us to perform task-specific synchronization. For example, suppose my task graph has 4 tasks, A, B, C, and D, and 4 dependencies. A runs before B and C, and D runs after B and C. To ensure correct execution, we need to wait for A to finish before launching B and C asynchronously. Similarly, before launching task D asynchronously, we need to wait for B and C to finish. As a result, by properly synchronizing tasks using future.wait, we can create a task graph dynamically. Let's take a look at the same task graph implemented using the C++ sender receiver model, which is a standardized abstraction for composing tasks and dependencies. Here we use a static thread pool to schedule tasks on a pool of worker threads. We create a sender task for A and synchronize its execution before launching 2 parallel sender tasks B and C. Then we use when all to wait for both B and C to complete before creating the final sender task D. Finally, we synchronize once more to complete the task graph. This slide shows the same graph but implemented using TPP library with task group, which is a class to create asynchronous tasks and wait for their completion. First, we create a task group TG and use the run method to create 4 asynchronous tasks A, B, C, and D. Similarly, we need to wait on A before running B and C, and wait for B and C to finish before launching task D. Again, this slide implements the same task graph, but using OpenMP's task dependency clauses, which leverages compiler directives to define tasks and dependencies for parallel task execution. Inside the OpenMP parallel region, we define dependency handles in 4 integers, AB, AC, BD, and CD, that represent the task dependencies from A to B, A to C, B to D, and C to D, respectively. Then we specify the task dependencies using in and out clauses when creating an OpenMP task. For example, task A has 2 outgoing dependencies on B and C. Task D has 2 incoming dependencies from B and C. With these OpenMP directives, the compiler will insert parallel code that launches asynchronous tasks and enforces their dependencies automatically for you. Finally, this slide shows the implementation, but using OpenSilk, which is a fork-join programming model that relies on compiler-generated parallel code using keywords like silkspawn and silksync. In this example, after running task A, we spawn a child thread on task B using silkspawn, continue with C in the main thread, and then synchronize both B and C using silksync before running task D. Similar to OpenMP, you need a compiler that supports OpenSilk syntax to run this code. So far, we have seen many different asynchronous tasking models to create task graph dynamically. While each has its own advantages in certain domains, they frequently come with the following limitations that prevent us from fully utilizing the potential of dynamic task graph parallelism. First of all, If you pay attention to these models that we just talked about, tasks and their dependencies are decoupled from each other during the task graph construction. And the problem is, if dependencies are not expressed alongside the task creation logic, it becomes very difficult for programmers to reason about the overall task graph structure. More importantly, without a clear dependency structure, the runtime may not have that many opportunities to optimize task placement and load balancing when constructing the asynchronous task. Second, correct placement of the wait call is completely left to programmers. This basically means, as a programmer, you must decide a correct synchronization order at the very fine-grained level. And in the worst case, the number of wait call will be the same as the number of task dependencies. And unfortunately, in practice, many applications only care about the completion of the entire task graph instead of an intermediate task, making such fine-grained synchronization and waiting really unnecessary, costly, and very easy to find bug. Third, limited support for building highly dynamic task graph. Highly dynamic task graph means those whose structure, dependency, and task content are highly dependent on runtime variables or dynamic control flow result. And this is very, very difficult for existing framework to achieve. For example, if you take a look at OpenMP, it is not a good fit for this scenario because it relies on compiler to generate parallel code, which is relatively static. You do not have that much dynamic information that appear at the runtime when you program your OpenMP program. Finally, some models may require a non-standard C++ compiler to generate parallel code, such as OpenMP, OpenSilk, which can have easily run into the portability issue across different computing platforms. Now, I'm going to introduce a new dynamic task graph programming model called AsyncTask to address these limitations. Before I talk about dynamic task graph programming, let's first understand the difference between static and dynamic task graph programming, TGP. All the examples we have discussed so far are dynamic task graph programming, DTGP. In static task graph programming, STGP, the execution follows a construct and run model. You build a task graph first and then you run it. That's the ideal model of STGP. On the other hand, in DTGP, dynamic task graph programming model, tasks can start as soon as their dependencies are met, meaning that the construction and execution of the task graph can overlap. For very large task graphs, this overlap can sometimes provide certain performance advantages over STGP. To better understand this difference, let's take a look at the static task graph programming in TaskFlow, which is a C++ library for task parallel programming. Suppose our task graph has 4 tasks, A, B, C, and D. A runs before B and C, and D runs after B and C. In STGP, you define this graph in a task flow object. Then you define 4 tasks in terms of C++ lambda function objects A, B, C, and D. And then you use the precede and succeed method to relate the dependencies among A, B, C, and D. When the graph is constructed, you submit it to the executor for execution, which manages a set of working threads to perform scheduling for you. As you can see, the construction and execution of these task graphs are separate from each other. That's the idea of static task graph programming. Instead of starting from scratch, we have built our dynamic task graph programming model AsyncTask atop TaskFlow, so we can reuse many of its facilities. Using the same task graph as an example, we create a task from a C++ lambda function object using the silent dependent async or the dependent async method if you would like to acquire additional future object that allows you to perform task-specific synchronization. When you create a dependent async task, you can specify arbitrary dependencies using C++ variable parameter path. For example, when creating task D, I pass B and C as the last 2 arguments, indicating that task D cannot actually start after B and C finish. More importantly, when you create a dependent async task, the runtime will start its execution immediately whenever its dependencies are met. So the task graph construction can now overlap with the task graph execution. If you don't want fine-grained synchronization, like waiting for a particular task in the graph to finish using its future object, you can use the method wait for all to wait for the entire graph to finish. And you probably already know DTGP needs a correct topological order to specify dependencies dynamically. This is because when you define a dependency on a dynamic task, the parent task of the dependencies must have already existed in a correct topological order. In our example, this means you can program dynamic task graph using the order either ABCD or ACBD, because both of them are correct topological orders representing your task graph. An incorrect topological order will prevent you from expressing a correct dynamic task graph. For example, if you create task D before B and C, there is no way you can specify the dependencies on B and C because B and C do not exist yet. So this is the major limitation of dynamic task graph programming. You have to know a correct topological order for your task graph before you create a dynamic task graph. Both methods in our model, silent dependent async and dependent async, can take a variable range of dependent async tasks. And this is particularly useful when a task dependency comes as a runtime variable, such as the task graph must be loaded from a file, which is only known at the runtime. In this example, we can create a vector of dependent async tasks and use it to specify the dependencies when creating another tasks. Well, this feature may look very trivial to most of you. Unfortunately, I found it very difficult to achieve when using existing dynamic task graph programming models or libraries because their task creation and dependency expression are decoupled from each other. For example, if your task graph comes as a runtime variable, it becomes very difficult to do it with OpenMP and the C++ sender-receiver model. One major advantage of DTGP is the flexibility for you to enable very, very dynamic execution that is completely driven by runtime or dynamic control flow results. For example, depending on the values of the variable ABC over here, I can create a totally different task graph. If A is true, I can create a task graph G1. If B is true, I will create a task graph G2 that runs after G1. Otherwise, I'm going to create a totally different task graph G3 and ask G3 to run after G1. Or, depending on the structure of a task graph, if G1 has 100 tasks, I'm going to run G2 right after G1. Otherwise, I will create a new task graph G3 and make G2, G3 run after G1. So this type of dynamic task graph parallelism and construction at runtime driven by dynamic control flow result, it's very difficult to achieve using static task graph programming model because you cannot decide the task graph structure upfront. As you can see from our programming model, AsyncTask does not touch data abstraction. This is a very important decision that we have made during the early stage design of AsyncTask. We want to focus on coarse-grained task parallelism instead of fine-grained data parallelism. The primary goal is to have users describe tasks and their dependencies in an expressive graph language using completely standard C++. With this interface, user can define function as a lambda and capture the necessary data or arguments, input arguments by themselves. And this is basically how std async, stud async is implemented, as we have seen before. And the advantage of this decision is twofold. First, users can retain full control over data layout and ownership, allowing them to optimize data structure and memory layout for their specific application domain. Typically the way you want to optimize your data layout, memory layout is completely depending on your application, and we do not want to touch it. Second, letting users decide how and where to store data keep async tasks very lightweight and non-intrusive. There is no need to modify your existing data structure in order to fit into our framework. And this is very different from existing models that count on data abstractions such as fast flow, TPP pipeline, requiring user to rewrite their code to library-specific data abstraction just because you want to program data or test parallelism using their libraries. Now, I'm going to talk about how we overcome some of the scheduling challenges to support our programming models. Our scheduler is built on top of TaskFlow's work stealing scheduler, which has two levels, task level and worker level. At the task level, the job is to decide which task to enqueue to which worker whenever its dependencies is satisfied. At the worker level, the job is to decide which worker to run which task whenever a task is available. And this is a masterpiece of work, and I cannot cover all the details in the interest of time. If you are interested, I encourage you to check out the original TaskFlow research paper that we published in TPDS. Instead, I'm going to focus on how we schedule a dynamic task graph atop this work stealing facility in TaskFlow. There are three scheduling challenges that we overcome. Number one is ABA, number two is data race, number three is synchronization. So ABA means dependent async tasks must exist correctly. We cannot specify a dependency that points to an invalid memory location. Data race, because task graph construction execution in DTGP right now can happen simultaneously. Multiple workers may concurrently access the successor of a dependent async task. We must prevent data race. Synchronization. Application may issue fine-grained wait call at any time in DTGP. So we need to ensure synchronization does not introduce too much overhead. Let's take a look at the scheduling challenge number one, ABA. Like I say, ABA means every time you specify a task dependency, such as the task B over here, that depends on A's finish, that task A needs to refer to the right task A. And this is because in dynamic task graph programming, when task A is created, it may start immediately and finish just right before you want to use it. Now, if A finish really quick and its resource are reclaimed by its running worker due to memory pool or object pool optimization or recycling style optimization, then that task A you refer to may not be the original one, right? Even though it has the same memory address. So this is the classical ABA problem. To solve this problem, we have introduced a spatial handle called AsyncTask that requires the application to retain a shared ownership of each task needed. This AsyncTask handles action like, basically it's similar to the share pointer to ensure tasks will stay alive when they are used. So with this shared ownership, we can guarantee that any specified task dependencies will exist correctly and will not have the ABA problem. The next challenge is data race, because multiple threads or multiple workers may simultaneously access the successor of a task when it finishes. In this example, both B and C may want to add themselves to the successor of A. Meanwhile, A may also want to remove its successors when it finishes. A very simple solution, of course, is to use a mutex to enable exclusive access. But mutex is quite expensive, especially when you have many dependencies on a task. Instead, we use a compare and swap operation with spinning to enable exclusive access. And this spinning process does not, according to our experiment, does not incur too much overhead because most task graphs in real world are very sparse. And if your task graph is very dense, probably DTGP is not the right solution for your application. The final challenge is synchronization. In DTGP, user can issue both coarse and fine-grained synchronizations at any time, such as waiting for the entire graph to finish using executor wait for all, or waiting for a particular subgraph to finish using future.wait. To synchronize the execution, one simple solution, again, is to use a mutex plus a condition variable to notify the application when the condition is satisfied. Like in most cases, the condition that is satisfied will be the number of tasks becomes 0. However, this log-based and mutex-based design or solution can be very expensive when the number of synchronization calls or number of tasks become very, very large. To reduce the synchronization overhead, we have leveraged C++20 timing variables to perform waiting and notifying operations, which basically allows us to move a lot of synchronization to user space rather than in kernel space. With all these ideas, our scheduling algorithm is completely log-free. There is no mutex involved, of course, with C++20. And we have published this algorithm in ICCAT 2023. And if you are interested, I encourage you to check out the paper for more detail. Now, I'm going to demonstrate the efficiency of AsyncTask. We have evaluated the performance of AsyncTask on both micro-benchmarks and the real-world application to study its performance without and with the impact of application tasks. In terms of micro-benchmark, we measure the performance on 4 commonly used task graph patterns. In linear chain, tasks are executed sequentially, one after another. In binary tree, each task spawns 2 dependent tasks. In embarrassing parallelism, all tasks are independent and they can run simultaneously without any dependencies. In random graph, tasks have dependencies assigned arbitrarily, representing irregular workloads. So in terms of the real-world application, we use AsyncTask to implement a task parallel static timing analysis application in VLSI, where we parallelize the timing propagation algorithm using AsyncTask. We consider the following baselines: OpenMP tasking, Parsec, OpenSilk, and AsyncTask LK and AsyncTask CV. AsyncTask LK replaced our scheduler with OpenMP's task scheduler, which leverages a log-based hash table to keep track of the relationship between tasks and their dependencies handles. This comparison basically allows us to measure how good our log-free scheduling algorithm is. AsyncTask CV replace our atomic variable-based notification algorithm with condition variable. This comparison allows to see how good our C++-based notification algorithm is. All the programs are compiled using GCC on G++12 with C++20 enabled and optimization flag O3 enabled. So the machine we tested is a 64-bit Linux machine with 128 gigabyte memory and 20 Intel i5 cores, each at 4.8 gigahertz. And all the experimental data collected over here is an average of 10 runs to reduce variance. This slide plots the performance comparison for the 4 micro benchmarks: linear chain, binary tree, embarrassing parallelism, and random graph. In general, AsyncTask is doing a very good job outperforming the baselines in nearly all scenarios. For example, in random graph, as we increase the number of tasks on the x-axis over here, AsyncTask scales much better than the other baselines, and the gap to OpenMP, marking the blue line over here, becomes larger and larger. And for a fixed graph at 2 million tasks, the runtime decreases as the number of threads increases, and the performance saturates at about 4 threads. And of course, this depends on the maximum parallelism available in your task graph. So similar data, similar trend can also be observed in other 3 micro benchmarks. We also measure the ease of use. Basically want to see how productive AsyncTask can give you. We measure the ease of use of this aspect of AsyncTask by surveying over 300 graduate students in my HPC course at UW-Madison. And basically, I took advantage of me teaching the high-performance computing and design a programming assignment, asking students to complete these micro benchmarks using 5 different DTGP libraries: AsyncTask, OpenMP, OpenSilk, Parsec, and std-async. By the end of this assignment, I asked students to rate each library in a score of 1 to 10, the higher the better. Here is the result of this survey. Most students find AsyncTask, OpenMP, OpenSilk, and std-async very easy to learn. They can complete most programs with AsyncTask and std-async. Debugging is a little bit challenging and disappointing, but students in general find still async tasks the easiest to debug because the expression of the tasks and their dependencies are not decoupled from each other. They have a better idea and picture of how the entire task graph looks when they program the task graph. In terms of the correctness, most students have hard time using existing library, but AsyncTask to complete the random graph benchmark, especially for OpenMP, we found over 90% of the students cannot get it right. Now, I'm going to talk about the evaluation on a real-world application, that is static timing analysis, or STA, which verifies the timing behavior of your circuit. And this is a very, very important application in circuit design automation because before you tape out the chip, you got to make sure the timing behaves as you want. We implemented this task parallel STA algorithm using AsyncTask, where the timing propagation algorithm is modeled as a dynamic task graph, where we propagate the timing data from the inputs of the circuit all the way to its output. For example, here I have a task graph representing the timing propagation of this simple circuit that has 5 gates. We evaluated the performance on 4 industrial circuit graphs, AES Core, DeskPerf, VGA LCD, and Leon 2. And the largest timing graph over here has over 4 million tasks and about 8 million dependencies. And as you can see from the plot, AsyncTask always outperforms the baselines, regardless of the number of threads that you use to run the task graph. There is a very consistent gap between AsyncTask and the other baselines. And this result highlights the efficiency of our scheduling algorithm. We also compare the performance with STGP implemented using TaskFlow. The purpose of this experiment is to highlight the advantages of DTGP, especially for large task graph, where overlapping task graph construction and execution can provide a very big performance advantage. In STGP, building a task graph is typically done in just one thread and does not overlap with the task graph execution. For a large graph like VGA LCD, which has about 400K tasks and dependencies, the time we spend on constructing the graph becomes non-negligible, taking almost 15%. In this case, DTGP will be slightly faster than STGP. Obviously, when the graphs are small, the scheduling overhead of DTGP will always overlap advantage because the overhead runtime scheduling to maintain the task dependency dynamically is non-negligible when the graph is small. In today's talk, we have understood the importance of asynchronous tasking with dependencies and went through several limitations of existing asynchronous tasking models. Then we have introduced a new dynamic task graph programming model called AsyncTask and showcased how we overcome some of the important scheduling challenges to support the model. Finally, we demonstrated the efficiency of AsyncTask on both micro benchmarks and the real-world application. Everything we discussed today about AsyncTask has been integrated to the open source project TaskFlow. In case you don't know, TaskFlow is a header-only C++ library to help you more easily parallelize your application using a task parallel approach. The project actually started in 2018 as a DARPA-sponsored project to help them parallelize critical design automation workloads that cannot be efficiently handled by existing methods. Using AsyncTask is extremely easy. You simply need to download the TaskFlow project and compile your program by telling your compiler where to find the TaskFlow header file. So this is a completed header file only project. That's it. There's no wrangling with installation. Finally, I would like to say thank you to all the users, all the people who are using TaskFlow in their projects. As I mentioned, TaskFlow is open source and it's being used by a growing number of people from both academia and industry, and we are always very happy to collaborate. The project will not be successful without a sponsor. We really appreciate the financial support from the funding agencies. With that, I'm going to stop here. I'll be happy to take any questions. Thank you very much.